Welcome, deep divers. So imagine this for a second. Right beneath the surface of our everyday lives, the very foundation of our energy supply.
Yeah.
It's quietly going through this absolutely huge transformation.
Huge. It's right. And it's not just about like how we flip a light switch anymore.
No, exactly. It's a shift that's going to impact, well, everything.
Yeah.
How we power our homes, sure, but also these massive data centers that are fueling AI. It's literally reshaping the landscape.
Mm-hmm. And that profound shift is exactly what this deep dive is all about today. The modernization of the energy industry. We've waded through a whole stack of sources.
Yeah, we have.
Industry leaders, magazine reports, expert insights, you name it. Trying to get a handle on the immense pressures on the grid, the surprising solutions that are popping up, and also the crucial lessons we can actually learn from data itself.
Right. How to navigate this really complex picture.
Exactly.
So our mission today is basically to give you a shortcut, right?
Yeah.
A fast track to being genuinely well informed on what feels like a super vital topic. So let's unpack this.
Okay. So maybe let's start with the immense pressure points. What's really pushing against our current grid? For decades, electricity demand was pretty flat, relatively speaking.
Stable, yeah.
But that has just changed dramatically. We're seeing this unprecedented surge. It's often called the electrification of everything.
And it's incredible when you think about the scale of it, isn't it? EVs, smart buildings, even this whole push for reindustrialization, bringing manufacturing back, all of that adds this significant sustained load onto the grid.
Right. But then there's the kicker.
Yeah, the AI piece, the absolutely unprecedented impact of AI and the data centers needed to run it.
Exactly. These data centers, they just consume enormous amounts of power. We're talking gigawatts sometimes.
Like small cities.
Pretty much, yeah. Comparable to small cities. Alan Swade over at GE Vernova, he observed that this AI demand, it wasn't really on the industry's radar like this before.
Nobody saw it coming this fast.
Right. But it looks like it's here to stay, for maybe a 10, 15, even 20-year run. And the projection is that electricity demand just from data centers, it's expected to double by 2030.
Double by 2030. That's
wow.
Mark McVeigh at Dominion Energy. He gave this example of 3 1-gigawatt data center sites going into just one area.
1 gigawatt each.
Yeah. And they put it in perspective. A typical nuclear site is maybe 2 gigawatts.
Yeah.
He basically said you're going to blow through that pretty quick.
Yeah.
So, okay, with that kind of demand, what does this massive growth actually mean for the grid overall? Are we even close to being prepared?
Well, it means the U.S. electrical infrastructure, the grid we spent something like 80 years building, might need to double in the next 15 to 20 years. That's just a staggering scale of growth, faster than anything we've seen.
Okay. And
it's not just about meeting more demand. It's also about the state of the infrastructure we already have.
The aging problem.
Yeah, the aging problem. About 70% of North America's core grid infrastructure is getting towards its end of life.
70%. That's a really shocking figure when you hear it like that.
Yeah.
I remember Christina Park from Skydio. She put it really bluntly. She said, all of our infrastructure was built at a time that it was just not meant to take the loads and the weather conditions and things that are happening today.
Exactly. And that points to this really critical shift in focus. We used to talk mainly about reliability.
Just keeping the lights on.
Right, keeping the lights on. But now the emphasis is really shifting towards resilience.
Which means getting them back on quickly after something happens, right? An event.
Precisely. Getting them back on fast. And what's making that shift so urgent? Well, you've got more severe weather events. You've got cyber threats.
Increasing all the time.
Yeah, they're increasing in frequency and intensity. So rapid recovery isn't just nice to have. It's non-negotiable now.
So things like mobile substations, stuff like that.
Yeah. Exactly. Proactive solutions like mobile substations that you can deploy quickly, they're becoming essential to get service back fast after a disruption.
Okay.
But this modernization, it's not happening in a vacuum right now. We're also facing some pretty significant supply chain and workforce challenges.
Yeah. The practical side.
The practical side. For critical gear, like power transformers, those big ones, lead times can stretch out 3 to 5+ years.
5 years just to get a transformer.
Yeah. And bushings, another vital component, they take 2 years.
2 years for bushings.
Yeah.
That's a long time to wait when demand is, exploding.
It is. And then there's the people problem. The workforce.
Right.
You've got an aging professional base,
Yeah.
a lot of experience heading towards retirement.
And it's hard to get new talent in.
Yeah, it's difficult to attract and train new talent.
Yeah.
So you end up with this significant skills gap.
Yeah.
Kevin Riley at Trantech, he noted how many experienced pros have retired, and the new generation coming in, well, they might not know nearly as much yet.
So that knowledge gap, how does that actually, impact things on the ground?
Well, it means critical institutional knowledge just walks out the door. Makes it harder to maintain these complex systems, harder to innovate. John Bucciarelli from SD Myers, he really stresses the importance of TED training, education, development.
TED.
Yeah, to try and bridge that knowledge gap. And it's not just about people, it's also about the actual materials, critical materials.
Like steel.
Specifically, grain-oriented electrical steel, or GO-DUIS.
Go-Bees. Okay. Sounds niche, but I'm guessing it's important.
Oh, incredibly important. It's basically the magnetic backbone of transformers, essential for grid reliability, for energy efficiency.
So what's the deal with GO-Ease? Why is it a vulnerability right now?
Okay, so global GO-Ease production, it was about 4.4 million metric tons in 2024. But here's the catch.
Uh-oh.
80% of that supply comes from Asia.
80? Wow.
Yeah. China alone accounts for 58%, Japan 13%, South Korea 6%. North American production, it only covers about half of our own domestic needs.
So we're heavily reliant on imports.
Very reliant, creates a single point of failure potentially. Ron Harper from JFE Shoji Power Canada, he points out that things like trade barriers, they just create extra vulnerabilities, extra costs right at the time when we need to be speeding up investment in these supply chains.
Okay, wow. So the problem is, it's immense. You've got surging demand, aging infrastructure, these supply chain bottlenecks, the workforce gap. Feels like a real uphill battle.
It does.
But okay, here's where the story hopefully takes a turn, right?
Yeah.
How are we actually tackling these challenges? Let's dive into the smart solutions, starting with AI.
Right. AI, it's often seen, like we said, as a demand driver because of the data centers.
Yeah.
But it's also proving to be a transformative force within the power sector itself.
Okay. Using AI to fix the problems AI is causing, sort of.
Kind of, yeah. It's helping optimize grid operations, from generation all the way to distribution. It's moving us away from just reacting when things break.
Reactive maintenance.
Towards predictive asset management. So, for example, Enel Green Power, they use AI to predict, solar irradiance, wind availability.
Get the most out of their renewables.
Exactly. Maximize output, help grid stability.
And it's not just forecasting, is it? I read National Grid UK is using AI for predictive maintenance, too.
Yeah.
Analyzing data from transformers, cables.
Yeah, to spot issues before they cause failures.
Before they break.
Right. It's a fundamental shift. It's like having a health monitoring system for the grid itself, predicting failures instead of just fixing them.
That makes sense.
And you see others, too, like California ISO, CAISO, and Germany's 50 Hertz. They're using AI for load and generation forecasting, helps them handle bigger loads, makes the grid more flexible, more responsive.
And AI is even showing up in, customer service.
Yeah, it is. EDF in the UK uses machine learning to spot irregular consumption patterns, maybe identify vulnerable customers who need help. Dubai Electricity and Water Authority, they have Ramas, which is this AI-powered smart assistant.
Like a chatbot.
Yeah, basically. Available 24/7 for customer questions.
Yeah.
But what's really fascinating, I think, is how AI's strategic advantages go beyond just efficiency.
Okay.
It lets utilities optimize their spending, both capital and operational, and crucially, it strengthens grid resilience. By enabling a faster response when disruptions happen. The sort of future vision here is AI making more real-time decisions with less human oversight. A truly autonomous grid, eventually.
That sounds incredibly powerful, but it also sounds like a massive leap.
Yeah.
What are the practical roadblocks? What stops utilities from just rolling this out everywhere? Is it just data or?
Well, it's all of the above, frankly. You've got challenges like data silos, data stuck in different places, not talking to each other.
Right.
Poor data quality sometimes. Big cybersecurity concerns, obviously.
Of course.
And that skills gap, again, needing people who understand both the power systems and the AI.
Right.
Interdisciplinary teams. But despite all that, digitalization, as Claudia Casoriano at GE Vernova emphasizes, it's absolutely key. It's the foundation you build everything else on.
Digitalization, right. And you often hear that phrase, utilities drown on data but starve on analytics.
Yeah, exactly.
Which really highlights this critical need for better data management. Getting all that silo data into one place, like data lakes, so you can actually fuse it, cross-correlate it, make sense of it.
Dea Bayumi at Hitachi, He stresses this need to shift toward comprehensive condition monitoring, get away from just doing inspections based on time, every 5 years or whatever.
Be more proactive based on the actual condition.
Precisely. And this whole idea leads us nicely into the concept of digital twins.
Digital twins. Heard a lot about those. What's the core idea there for the grid?
Well, Balavinayagam describes it as basically modeling the physical behavior of an asset like a transformer over time, using real-time data, historical data.
See how it's aging.
Yeah, to understand how it's aging, how it's performing, and then guide your actions. It shows you the difference between the system as designed and the system as operated in the real world.
So it's not just a static model, it's a living representation.
Exactly. Dynamic living representations of physical assets. That's the real insight.
Okay, so if that's the goal, this digital responsive grid, what does a sort of blueprint for getting there look like? Especially creating these interconnected systems. Matt Schnug at Schneider Electric, he suggests we should look at other industries.
Yeah, like software, financial services, healthcare. See what lessons we can learn. He outlines this evolution, right, in software development.
How it changed over time.
Yeah, from like machine level programming, very basic, direct control,
right,
to operating systems, more abstraction, managing resources,
okay,
and finally to ecosystems. Think app stores, platforms.
Where everything connects.
Exactly, where everything connects and builds on each other.
And the energy industry needs to make a similar jump.
That's the argument. Industries tend to move from these isolated, hard-coded solutions towards integrated platforms, and then finally to these open ecosystems using embedded intelligence. So, for the grid, Schnug identifies 5 foundational principles.
5 principles. Okay, what are they?
1, prioritize openness. Shared data models, APIs.
APIs, application programming interfaces.
Yeah.
Ways for software to talk to each other.
Right. 2, frictionless availability. Make sure products work together natively out of the box.
Interoperability.
Exactly. 3, embed resilience and risk management right at the core, not as an afterthought. 4, enable ecosystem collaboration through strategic partnerships. No one company can do it all.
Makes sense.
And 5, simplify ecosystem growth. Use modern tools like infrastructure as code.
Infrastructure as code,
yeah,
meaning you manage your IT infrastructure using code, like software, instead of manually configuring hardware.
Yeah, precisely. Makes it faster, more repeatable, scalable.
Okay, so if I'm getting this right, it's about building this flexible, interconnected digital nervous system for the grid, allowing all the different bits, components, companies to talk seamlessly, adapt quickly. That sounds, well, powerful.
It's a powerful vision. And Martin Robinson at Iris, he offers a concrete example with their eSentry system.
eSentry, what's that?
It's basically a Gen AI-powered data management solution. It's designed to connect to any data source, sensors, enterprise platforms, whatever.
Okay.
And then give you actionable insights, but in a conversational way. You can sort of ask it questions.
Interesting. But he mentioned a barrier, right? Trust.
Yeah, a critical barrier. Getting trust from the operators, the people
Yeah.
who will actually use it.
Why is that trust so crucial for adoption? Seems obvious, but...
Well, think about it. These operators, they've relied on their experience, their traditional methods, for decades.
Yeah, gut feel sometimes.
Exactly. So for them to fully buy into an AI-powered system, they need to really, truly believe it's accurate, it's reliable, it's secure. It's not enough for the tech to just be good on paper.
It has to prove itself in the real world.
It has to prove itself, yeah. And integrate smoothly with how they already work. Okay, so finally, let's look quickly at how smart manufacturing and supply chains are trying to evolve to meet all these demands.
Like the physical stuff has to keep up too.
Absolutely. Those core materials we talked about, GoES, and also amorphous metal, or AM.
MAM.
Amorphous metal, another key material for transformer cores. They're crucial. And there are new U.S. Department of Energy regulations coming in 2029.
Regulations driving change.
Yeah, requiring higher efficiency, which means things like using thinner steel, getting lower core losses in the transformers.
Okay, and this is where Microtool and Machine Ltd. MTM comes in.
Yeah.
With their flexible manufacturing idea.
Exactly. MTM. They've got this strategy for flexible machine deployment, basically allowing transformer manufacturers to invest in stages rather than having to buy a whole new massive expensive line up front.
Makes sense. Spread the cost, adapt as you grow.
Right. They've identified 3 key upgrade paths.
Path 1.
Path 1 involves portable add-on modules, things like wire flatteners, cold welding systems, bending fixtures.
Small additions to existing machines.
Yeah, relatively low-cost additions, give you quick wins on quality, efficiency, easy to retrofit.
Okay. Path 2.
Path 2 focuses on multi-coil manufacturing, so upgrading existing machines so they can wind more than one coil at the same time.
Doubling or tripling output, maybe.
Potentially, yeah.
Right.
Doubling or tripling output without needing entirely new, expensive winding machines. It's about scaling smarter.
Got it. And Path 3.
Path 3 integrates laser welding for the internal bus bar connections.
Automating those tricky internal connections.
Exactly. Automating those precise connections gives you consistency, reduces the need for skilled manual labor, which we know is a challenge.
Right.
And there's a real-world example, alpha transformers. They use these kinds of phased upgrades. Started with a combined winder, added a wire flattener and cold welder, later added a dual coil winder, a semi-automated TIG welding cell.
And the result?
Boosted their quality, boosted output, gave them more flexibility, all with minimal disruption, because they did it in stages.
So the real impact here is enabling manufacturers to ramp up production more efficiently, more cost-effectively, to meet that surging demand we talked about.
That's the idea. It sounds like these innovations in manufacturing are absolutely vital, not just for individual companies, but for the resilience of the whole energy grid supply chain.
Yeah. And what seems key here, according to Ron Harper again, is collaboration.
Absolutely. Between industry, utilities, government, building these resilient supply chain ecosystems, supporting domestic capacity, yes, but also strengthening ties with global partners where it makes sense.
Okay, so we've covered the pressures, the solutions. But now, as we navigate all this information, this transformation, you mentioned there are hidden traps we need to watch out for.
Yeah, absolutely. Tony McGrail from Doble Engineering, he poses this really core question. What's missing?
What's missing?
Yeah. This principle, it's often called survivorship bias. And it can lead you to completely false conclusions if you're not careful about the data you don't have.
Survivorship bias. Okay, explain that a bit more.
Yeah.
Like the Darren Brown coin trick you mentioned?
Exactly like that. The 10 heads in a row trick.
Mm-hmm.
You, the audience, you only see the one successful trial where he gets 10 heads.
Right. Looks impossible.
Looks impossible. But what you don't see are the hours and hours, maybe hundreds of failed attempts before that.
The missing data.
The missing data. It's just probability and stamina, but because we only see the survivor, the successful attempt, our brains fill in the gaps and think something extraordinary happened. We assume we saw the whole story.
It's deceptive because it plays on how we naturally think.
Very deceptive. And a much more impactful, frankly chilling example is the Carter racing case.
Which wasn't actually about racing, right?
No, it's a famous Harvard Business School case, but it's a disguised account of the data analysis, or lack thereof, before the Challenger space shuttle disaster.
Oh, wow. Okay.
Initially, the engineers, they were shown data only from launches where the O-ring gaskets had failed or shown damage.
Just the failures.
Just the failures. And looking only at that data, there wasn't a clear link between the launch temperature and the O-ring failure.
Okay.
But when the missing data, the data from all the successful launches, was added to the chart,
What happened?
a clear correlation just jumped out. No successful launch had ever occurred below 65 degrees Fahrenheit. The Challenger launched at 36 degrees.
Oh, my God. So the missing data held the key.
The missing data held the absolute key. The consequence of not seeing it, of not asking what's missing, was catastrophic disaster. It's just a terrifying reminder of how incomplete information can lead to fatally flawed decisions.
That is.
Yeah.
A very stark reminder. And there was another example. The stock-picking cows.
Right, the stock-picking cows. A bit lighter, but illustrates the same point. A TV crew claimed these amazing returns from a portfolio supposedly picked by cows throwing darts or whatever.
Sounds ridiculous.
It was. The answer was they'd secretly run like 20 different portfolios. They just filmed and broadcast the results of the one that happened to do well by pure chance.
The survivor.
The survivor. Again, you only see the winner if you don't actively ask, what am I not being shown? What's missing? It's a good lesson in skepticism for anything that looks, a bit too good to be true.
Definitely. Okay, so that's missing data. But you also mentioned a trap around the imprecision of data we do have.
Yes, exactly. Even when you have the data, understanding its limitations, its inherent inaccuracy, is crucial. Take dissolved gas analysis DGA in transformers. It's a key diagnostic tool.
Right, testing the oil for gases that indicate faults.
Yeah, and the results are often visualized using something called the Duval triangle. But here's the thing. The measurement itself isn't perfectly precise. A true value might vary by, say, 15%, even in a good laboratory.
Okay, 15% variance.
Or, if you're using an online monitoring system out in the field, that variance could be as high as 35%.
35%, that's huge.
It's a really significant range. And that level of imprecision can lead you to completely different diagnoses based on where that measured value falls within its potential range.
So you might measure a certain gas level, but the actual true level could be 35% higher or lower.
Exactly. And depending on where that range falls on the Duval triangle, it might push you from diagnosing, say, a minor discharge of low energy into a zone indicating a much more serious type of fault, or vice versa.
And the consequence of that misdiagnosis could be massive, right? You might take an expensive transformer offline unnecessarily, or worse, leave one running when it's actually close to failure.
Precisely. You make an incorrect decision about whether that asset needs immediate, costly attention or if it can keep operating safely. The risk is significant.
Okay. And this applies to other things too, like those health index scores.
Yeah, absolutely. Health indices, where you try to boil down lots of complex data into a single score, maybe 1 to 5, representing the asset's condition.
Simple and easy to understand.
Simple, yes. But dangerous if you're not careful, because that single number can completely mask the inherent imprecision of all the underlying measurements that went into calculating it.
You lose the nuance. You lose the uncertainty.
You lose the uncertainty. You get this false sense of certainty from a single number.
So the key takeaway here seems vital. It's not just about getting data. It's about understanding its quality, its accuracy, its potential range.
Yes. Without knowing the accuracy of your measurements, without considering the missing data of that imprecision, your diagnostic results, the decisions you make about managing your assets, they can be poor, even inappropriate,
Leading to big consequences.
potentially very significant consequences. It really underscores why you need to be able to see the raw data sometimes, or at least have an audit trail showing how conclusions were reached, rather than just trusting a simplified final number blindly.
Wow. Okay, what a deep dive this has been. So we've seen the energy grid's transformation is incredibly complex, it's urgent, it's being driven by tech, by people, and maybe most importantly, by data. We've looked at the immense pressures that surging demand from AI, the agent infrastructure, the tricky supply chains, and also the really innovative solutions emerging. AI helping manage the grid, digitalization, platform thinking, smarter manufacturing.
Right. And crucially, we've tried to shine a light on those hidden traps of information, survivorship bias, data imprecision, really emphasizing how important it is to ask what's missing and to understand the limitations of the data you do have before you make those critical decisions.
So hopefully you listening now have a much clearer blueprint, a better framework for understanding these really profound shifts happening in the energy industry.
Yeah, hopefully it provides a good shortcut to getting informed.
Absolutely. So as we wrap up, let's leave you with maybe a provocative thought to mull over, building on that think twice principle from Tony McGrail. What critical decisions are you making? In your own life? Maybe in your work? Where might you be unknowingly missing some crucial data? Or maybe overlooking the full, messy, imprecise picture?
That's a great question.
How might you consciously start asking, what's missing here? And, okay, what's the actual imprecision when you're evaluating information from now on? Something to think about.